Okay, 7:30. Let's get started on today's topic. Today is the last one of this module, parallel processing. This is parallel processing 2, lecture number 18. Next day, we'll shift our gear towards the another important component of computing system, which is memory hierarchy, caching, and virtual memory. That's a completely separate topic than the processor. So far, by today, we should be done with all this processor architecture and system architecture as such. Any question before we start discussion, anything on this topic? Let me check my discussions on the canvas. There is any? Nope, there is none. So just remember, there are three parts of this lecture 18. One is the first as the cluster computing, and second part is the new architecture, and third part is a little bit unrelated but also relevant in today's market is the vector processing, array processing. All these graphics chip you are seeing and some AI chips coming from the NVIDIA's are fall into that category. uh, about the cluster computing, it has a very interesting history. Like when the high performance computer started to grow in the market, especially with the internet boom during late 80s, 90s, uh, different company actually put their effort to make big, huge machines, SMP style, lot of cores, lot of processor on the board, and they want to crunch really faster number to serve the internet community. There are different companies where they're player where they're like HP, Sun Microsystem, Digital Corporation, Silicon Graphics, those big names. And then eventually Sun Microsystem became like a big player in the market during that time, and somewhat HP's also. There was IBM too at some point of time. Then comes that economic downturn during 2000, 2001, 2, which is like dot-com bubble burst. In the economic market, that's what referred to. And during that time, what happened, these big efficient SMPs actually cost much more dollar. Right? Ultimately, the end industry want to use some machine for their data crunching, for their simulation, for their internet service, and all this stuff. But alternate solution was being looked after, sought after during that time, saying that, hey, these are really expensive machine. We cannot afford in this economic downturn because we don't have money to spend to come up with. And we also see there are like cheap machines like personal computing PCs. They are really cheap compared to these data server machines. So is can we do anything like throw in like maybe hundreds or 500 of this cheap machine and come up with the similar performance range, similar performance, or at least comparable with this big gigantic machine? And that's the start point of ramping up this cluster computing market, where the main philosophy is that fill your data center with very cheap machines, and then uh, through this parallel computation and job distribution and all this stuff, make sure you are at par with those big efficient SMP style machine. And that's where the declination of this SMP machine started. And 2009, about that, Sun was bought over by the Oracle. Oracle's dream was to become a next IBM, who supplies the complete full stack of the solution from the hardware to the database to the software. But that also didn't fly that much, again, because people see is that, hey, with this cluster computing philosophy, we can do comparable performance with a less cost. So eventually Oracle stopped producing this big server. Their other hardware division, I think it's shut down now. IBM, I'm not sure what is happening to the IBM. Probably they also came out of that market. Similar with the HP, they're more concentrating on this low-end server and machines. Yeah, so that's the one thing I wanted to share. A little bit of information from the past, and then people started to look at this cluster computing system. It is runtime wise, it is efficient, but if a program needs a big chunk of memory, which is more than one specific machine can serve, then cluster computation or cluster system cannot be applied, or it cannot serve that type of processes where it needs really big memory, chunk of memory. So for those type of applications, NUMA architecture comes in. Like it is kind of a hybrid between SMPs and the cluster, where you have the machines, smaller machines with small local memories, but this system actually provides the remote access to the memories as well, so that it is presented to the user as a big chunk of memory, which is summation of all the smaller node memory. And one process can actually access them as in one unified big memory. That is the whole philosophy behind the NUMA architecture. It has implication though on the program runs, and one using NUMA environment, the application writer has to be very careful about their memory consumption. Otherwise, it can actually slow down their performance dramatically on this. So we need to basically make some checks and balance on the NUMA system of that. But essentially, like if a program demands huge amount of memory, which is beyond scope of one specific local memory, one machine, then NUMA architecture is best to serve that, hey, it is actually providing summation of all the memories in that cluster as a single memory. Kind of giving a view of the SMP, give a feel of the SMP system in that architecture. Question? No? Okay, then let's do one small math problem around this NUMA architecture. Let's say, let me share my board. Okay. Let's say there is a NUMA computer cluster having like 200 computing nodes, and each node is associated with 128 gigabyte of RAM. Like 200 computing node, 200 machine, you can see, and 128 gigabyte of RAM. An average local memory access time is 50 nanosecond. And average remote memory access is 180 nanosecond, because it's this network communication traffic, all these things are involved in that process. Assume a program is running on one node in this cluster and it consuming total of 233 gigabyte with the local memory occupancy of 100 gigabyte. Now, if there are 1 million memory access in this program, with the probability of accessing a remote memory location is 0.25, then what is the total times the program is in accessing the memory in millisecond unit? So we're not talking about the rest of the execution time, etc. We are just focusing on how much time it's spending on accessing the memory. So this is a problem, and let's do it in a group, in a breakout session, and then we'll come back with the solution discussion. Let's take about 15 minutes on this problem. And let's say, let me just redistribute some of the student. Okay, so here it go. Okay, let's wait for people to come back from the breakout room and we can discuss our solution observation. Okay, I think everyone is back. Okay. How about Isita? Did you get a chance to work on this problem in your group or yourself and want to
Yeah.
share? So what's
So
Mhm.
I guess I'd done the problem set. So I'm sorry about that. So I guess the number of access to the remote location can be calculated by multiplying the 0.25, which is the probability, times the 1 million memory accesses. So that's 250,000. And then the access to local memory is the difference of that using the probability.
Okay.
And you use the, so going back to the remote memory access time, that's 180 nanoseconds. You multiply that with the 250,000, and that comes out to be 45 million nanoseconds.
Mhm.
And consequently, you use the 50 nanoseconds for the local memory access, and you do the same by multiplying it out, and that's 37.5 million nanoseconds.
Mhm.
And you add them together, and then that gets you 45 plus 37.5 million, which is 82.5 million nanoseconds.
Right, exactly. Thank you very much. They are basically you're talking about the millisecond in that case,
Oh,
million,
sorry about
right? So you're right. Thank you very much, Isita. For others, like these, she is right. And it's basically something like this, what she described as a problem. So what she did is basically we have already known that, let me share this thing. Okay, so here we have already given is that you have these 100 GB is local occupancy, right? And 230 GB is a remote occupancy. But that information is not much needed. It's all it needs is that your probability of remote memory access is 0.25 of 1 million, which comes out to be 250K, and the uh, local memory location would be rest of them, which is 750K out of 1 million. Then we just simply multiply the remote memory access multiplied by average access time, which is like 180 nanosecond, which comes out to be about 45 millisecond. And rest of them are local memory access, which needs 50 nanosecond in average. So we multiply that 750K with 50 nanosecond, which comes out to be 37.5 milliseconds. So overall, 45 plus 37.5 millisecond is 82.5 millisecond. So that's the time this program will spend in accessing the memory. Question? No, no questions on this topic or anything else. How is the project coming up? Project 3 is according to my schedule. Seems like by next week you should be done with the implementation of the project, and then you have 2 more days, like I think April, May 4th is the project 3 submission. So by April 27, after that, you should be done with your implementation project 3 part 4. So where are you in that respect? Why don't I just make a poll? Okay, just Let's make an anonymous poll and see what happens. So this is an anonymous poll. You can just, it's asking for where are you with your current project, haven't started yet, started but failing behind the schedule, means you have started but not quite up to the today's till today's lab. So basically you are falling behind. Then you are at par, done with the task to date, and last but not the least, completed. You are already done with all the implementation. So let's see how where we are as a class. Let's take about a minute on this. So I have 28, 29 of 33, 3 more percent to go. This anonymous polling. Maybe 1 more person to go. I'll wait a couple of more seconds. Okay, I think all of you have voted already. Let me share the result with you. So you see that about 13 people out of 33, 39% said haven't started yet. Please start. It is going to take time to like work on this project. So please start if you haven't started yet. Each of the lab is your task. 58%, that is majority, have stated that you have started but failing behind the schedule. So please keep up your pace. Maybe by this weekend, just make yourself up to date with that, with those labs. And once it completed, wow, okay, congratulations. You have done it, and just make sure you have done the report and everything. That's true. No one is done with the task to till date, so everyone else is falling behind or at least they haven't started. Please start. Please pick up the pace. Make sure you are on time on this May 5th, April, May 4th deadline. Okay. Uh, so with that, I would say then let's stop tonight to go back to work on your lab, on your project. And for the next day, we'll start on this memory hierarchy. That's very interesting topic. Caching, another interesting topic, and virtual memory. That's basically what we'll see. Virtual memory is mainly it is a part of the operating system class. So we won't be discussing in details about that operating system part, how to manage the memory using the virtual memory scheme. What we'll discuss here in this class, what is the hardware support needed to support the virtual memory system in the modern computing architecture. So that's the part we'll pick up. So this virtual memory as a whole, if you want to look for the topic, majority part sits on your operating system class. Okay, this class we discuss just on top of that, what is the hardware need to support for virtual memories. All right, so saying that, let's begin this new module next day. There is a quiz coming up, will be open up tomorrow morning, 6 a.m. And you need to submit it by Saturday, this Saturday, midnight, 11:59 p.m. Make sure you turn it in time, don't miss it. Okay, quiz number 3. Any question, any last minute question before we?
Yeah,
Yes.
Professor, you said you were going to update the scores for Project 2 last time. I still can't view mine.
Hey, really, I thought I did that.
Yeah, I can see mine either.
You cannot see? Okay, let me see what happened. Hey, what happens? I thought I opened up for everyone. Oh, why it is not showing? Okay, let me do that now and you try it, okay? All right. Something happened. I thought I did that last time. Okay, I just clicked on this post grid again. Okay, it says a success that had been posted. Can you please check?
Yes, mine are in.
Okay, okay. Maybe something happened, or maybe I thought I did, but I forgot. Thank you for reminding me.
Problem.
Okay, any other question from any of you? Okay,